So, hello everyone. Today I will explain a little bit about the experiment, about the process, and then I hope you can watch the full video. But if you already make or build some PCB design before using the CAD software like Altium or KiCAD or something, you can skip some of the part of the video and you can try again. And more you're learning, it will be making you better designing the PCB. Because I assume that all of the student not equal, not the same about the knowledge of the designing PCB. So I will explain in this presentation uh, more detail. So um, I will explain again about the buck converter topology. So the buck converter actually is consists one switch, one diode, one inductor, and then one output capacitor, and then the load. So the inductor and then the capacitor uh, will be the filter. So the switches will be controlling the output voltage, and then because the output voltage will be uh, like square wave, it needs to be filtered to be almost constant voltage, output voltage. So this is will be on off, and then this switch we need to control with some PWM generator. So this is the main component. So that is the short explanation. And then the next step is we need to install a CAD software. So CAD software is a program where we can design the PCB. So there is so many, but in here I choose KiCAD because it's open source and then free, and then it's very light if I compare with the others like Altium. So you can download from here and try to install. So I will give some example. So you just need to open your browser and then just write KiCAD download, and then you can choose Windows, Mac OS, depends on your operating system, and then you just open here and then you can choose the link. It's about 1.3 or 1.2 gigabyte. So yeah, it start to downloading in here like that. Okay, we back to the presentation. So after you install the CAD software, we can try to the next step. So I will explain again about the MOSFET. Actually, the professor already explained it on the class, but I will explain to make you remember again. So in here, majority of the converter right now is using NMOS because if we compare the N-channel MOSFET and then P-channel MOSFET, N-channel MOSFET will be have more advantages, many advantages that it will be so long to explain. But so I will explain the work of the N MOSFET. So the MOSFET will be our switch on the circuit. So this is the N-channel MOSFET with body diode. Right now, majority of them will be including the body diode. So this is the drain, source, and then the gate. So how we control the open and close of the MOSFET is by giving some voltage to the gate. So we need to give some voltage potential between gate and source. That's why it's called VGS. So by controlling the voltage between gate and source, we can close and open the like a valve between drain and source. So when we put uh, 0 volt on the gate, the between drain and source will be cut off. So there will be open circuit in here. But when we put some voltage, will be closed circuit. So the current from drain can be flow to the source. So in ideal condition, the voltage, the value of voltage that we give to the gate will be linear by how many current that can be flow. But in reality, there is some non-ideal characteristic. So you can read more about this in the book about power electronics. But usually, to operate the MOSFET efficiently, we need to give some voltage between 10 until 15 volt to reduce the internal resistance. So it will be on the minimum internal resistance when turning on. So to control the N channel MOSFET, we need to give the VGS some voltage. To give the gate some voltage. But because some of the circuit topology, the source sometimes can be not in the same path with the common ground. So this sometimes can be flowed. In our case is on buck converter. So because this ground is not connected to the source of the MOSFET, so the source of the MOSFET is not on common ground, so it will be floating. To solve that problem, we can choose by using isolated DC-DC converter. So we provide another voltage source only for the MOSFET. So the voltage source should be isolated between the input and then the output. And then to drive the MOSFET, we need what is called MOSFET driver, because some of the PWM generator or microcontroller cannot drive the MOSFET directly. Because if take example like maybe Arduino or STM microcontroller or ESP right now, all of them will be outputting only 3.3 volt. But the MOSFET need between 10 until 15 volt, maximum 20 volt. So how to make 3.3 into 10 until 15 volt? We can use what is called MOSFET driver. So it's like a buffer, like a bridge between the PWM generator and then the switches. So for the voltage source, we can use isolated DC-DC converter, or we can use bootstrap capacitor. Depends on what you need and then the circuit design. But the easy way is the isolated DC-DC converter. And then the next, we need to build the schematic. So I will recreate this schematic. So first, you open the software. So after you download it and then you open the software, you will make the software like this. So there is schematic editor, symbol editor, and the other stuff. But for right now, we can just click this file, new project, and then you can put anywhere. You need to make some project name. I will create again buck converter 2. So you don't need to be care to make a new folder because it will be automatically create a new folder for you. So just save. Tada, and then you will have these two files. So the bottom file will be for your schematic, and then the upper file will be for your PCB design. So first we need to open this one, and you will be made like some paper or drawing sheet. So we can try to start drawing like the schematic before. So to add the component, you can click this one, the symbol. So we need to add symbol of the component. So we start from the component of the buck converter. So we need to wait a while to loading the footprint. So in here there is so many component that you can use, but for a fast way you can just click here and type. Like we need some switches, some MOSFET. You can just use MOSFET, and then there is so many MOSFET or here. But in here, usually I will use this one for only the symbol, because majority of the MOSFET will be same type. So we will use IRF 540N. So this is to be our MOSFET, our switches, and then we need another one component. We need a inductor. So the inductor will be symbol L. So in here you can see the symbol on the schematic. So we need to put maybe like here. Oh, so you can rotate the symbol before you press it by press R on the keyboard. So you can rotate the position like this. And then we need some diode, D for the diode, like this. And then capacitor. So for the capacitor, you can choose the polarized or unpolarized. So it depends on your decision. So we can place here. Okay, right now we have the major component of the circuit. Right now we need the output and then the input for the circuit. So for the output and the input, it on the different button below the component button, you can add power symbol. So in here you can open the power. So there is a lot type that you can use. So maybe because our design will be inputting 24 volt, so I choose this. Maybe I can place here. And then we need some 5 volt, because I forgot to tell you that our design will be 24-volt to 5-volt output, and then we need some ground symbol here, and then you can just copy it by using Ctrl C and Ctrl V. Okay, so after placing the symbol, right now we can put some wire to the component. So we can just click here and drag the wire to its component like this. You can just move up a little bit. Because sometimes I want to look more good to be see, so yeah, we can do like this. Okay, maybe it's not very pretty to be seen, but it's okay. So we have the major component of the buck converter. We can move it to here. After we make the major component of the circuit, we need to make the driver and then the voltage source for the MOSFET. So in here, we will use the MOSFET driver, what is called from HCPL. So actually it's 3180, but from the default KiCAD library, they didn't have this, so you need to add manually. But we can use the similar component that is called HCPL 3120. So you can see the schematic and then the footprints on the PCB. It's same like what we will use later. So we can just put in here the component. And so I forgot to tell you that when you place like this, if you click again, they will open the symbol page again. But after this, you need to press escape button, so it will be back to the normal cursor. So after we place the driver, we need the voltage source, the isolated DC-DC converter. So I will use what is called ITQ2409. So actually it is not exactly this type of isolated DC-DC converter, but because the footprints is the same with what we will use on the circuit, so I just use this one. So you can just click this and maybe put in here. So I hope that you understand the general how to use this software. So I will make it a little bit fast, so we can this more faster, because you will getting bored when see video too long. So I just put here, and then for the input of isolated converter, we will use the same input voltage, so 24 volt. Don't forget your ground, copy it and then paste in here. Oh, this is and then for the input driver, we need some resistor. So open again, resistor. You can choose the small or big or large, depends on unit, but we can use the big one. So rotate it and then put like this. Okay, so like this. Before we continue, I will explain a little bit about what is called label. So global label. So you can click this one and then you will have this page. You can put the label name in here, depends on what you need. So this one, yeah, like this. Okay, so what is the function of label? Actually, label will be make your schematic more clean, more easy to understand, because this is like a sign that this this wire is have the same connection with this wire. So actually is it's like a wire that connect to this wire, but it's unseen. We cannot see by using the label, so it will be more prettier and more clean to see. That's the main function of this label. So we need another label for our driver input. So we can change the name, double click, maybe PWM, like this. Okay, and then for the output of the isolated, we need some capacitor just to minimize the ripple of the output for the MOSFET driver. So we can put some capacitor again. We can use the non-polarized like this, and then this should be connected to here. And then if you remember that we need some voltage source to another voltage source for controlling the MOSFET. So the voltage source should be between G and S, gate and source. So the ground of the output of our voltage source should be connected to this source. So we need some another label like this, put here, and source. And then we copy this label to here. You can put maybe in here, like this. And then I forgot to tell you that to make our measurement equipment to be easy to use, we need some pin that connected to the gate line. So we can just delete this wire, and then we put some pin that we can jumper. So in here I will use pin, 3 pin. So like this. Before or after the resistor? Maybe better before. After, yeah, better like this, maybe. So this should be connected like this. So when we adjust the duty cycle, we can remove the jumper, so it will be not affecting the circuit directly. So it will be not sudden change. But actually, it's okay, but it will be make our experiment more safer or more easier. And then when two pin is connected by the jumper, we can measure by using the other pins for the oscilloscope probe. And same with the source, but for the source we just need one pin. Open connector like this, one pin. Yeah, ta-da, like this. And then like this. And then this is for the driver, and then the voltage source for the MOSFET. So we need the PWM generator. In this case, right now we will use what is called TL494. So this IC actually is already pretty old, but is still capable to drive some half bridge or push-pull converter. But so yeah, this is have two modes, what is called single-ended and then push-pull. So when on the single-ended, because this control IC have two outputs, so when the single-ended, two outputs will be outputting on the same phase. But when push-pull mode, it will be the phase will be different, like 180 degrees, and it have a dead time compensation and then the other stuff. So even this is pretty old, but it's still capable to drive some converter. But I will not talk very deep about this IC because it will be take so much time. So you can just follow my design just like this. And then this should be go to same with this and these two, and then all of them connected to the ground like this, and then C1 and C2 will be connected together, and E1 and E2 same, and then we need some resistor, so we can copy from here and put in here for the 2ion minus, and then we need some capacitor for the CT. So C connect to the CT like this, and then of course we need voltage source and then the ground, because this IC can have input from I forget, but it's up to 40 volt. So yeah, it's pretty good. Put ground in here. So to I forget to zoom out and zoom in, you can use scroll on your mouse. And then we need what is called potentiometer or variable resistor, like this. You can put here, and then we need another one. We can just copy it, so it will be more faster. And here you can see my schematic on the presentation slide. You can pause it and then try and make it so it should be like this. And then this should be connected to the ground, and then this should be connected to the ground too, and then this too connect to the ground, and then this should be connected to the reference, like this. And then this should be connected to the reference too, like this, and then this too, reference. So this is for the, so this potentiometer and this potentiometer, so this one it will be used for controlling the duty cycle, and then this one will be used to controlling the frequency of the PWM signal. So C1 and C2 will be our output input, and then E1 and E2 will be our output. So we need to input in some voltage to the C1 and C2 like this, our voltage source, and then E1 and E2 will be output in the signal. So this signal will be used for the input of the MOSFET driver. So we will giving some same label in here, PWM. Yeah, like this. Okay. And then the next thing is we need to give it's our input and output some connector socket. So we can open again and just use con for the connector, same like connector pin, but we can use socket. So for we need 1/2 socket for the input and then the output. So we can just put it like this, and then we need another one, just copy it like this. So for the input, for the 24-volt, we can put like this, and then we copy the ground like this and just connect it, and then we can copy for the 5-volt, same, maybe like this, or you can just pull up, pull down. Yeah, let's undo this, so make it more, yeah, like this. So it will be more pretty to see. Yeah, so yeah, so this is the main schematic of the buck converter, including the driver and then the PWM IC. I forgot that in practical application, usually we need to put some another capacitor for the input, because the input side sometimes can have some noise or ripple voltage, so we need to stabilize the input voltage by using the capacitor. So it's okay, yeah, like this, it's okay, don't worry. So let's check again. see. Okay, I think everything is clear. After this, you can click save on the left top side, save changes. And then the next thing you need to do is open this, fill in schematic symbol reference designators. So this will give the components number, so it will be give the component number automatically. Actually, when we put some component, it already do it automatically before, but we just in case there is some error, we can make sure again by click this annotate. So after do that, we open this symbol, what is called run footprint assignment tool. So open this, you will meet by this page. So previously we just make the symbol for the component, but we don't assign the footprint. So we don't know the component type of the component type of the symbol, so we need to assign it. So in here there is a lot of footprint that you can choose, so you need to be careful when you choose it. So when we choose the footprint, we can see the view of the component. Like in here, maybe we need some connector, we can just right click. In example, this is right click and view restricted footprint, it will be open like this. So you can see the actually footprint that will be put on the PCB. So you can choose the better one. Usually I will just make it side by side, so it will be more easier like this. Yeah, so there is a lot of things you can choose. So okay, we will start from our capacitor, the C1. So we need to see our this one. So C1 is our input, C3 is our output, and then C2 and C4 is capacitor for the isolated DC, and then for the PWM generator. So generally the capacitor for the low voltage, for the more lower signal, like controlling signal or the MOSFET, can use a smaller capacitor. Usually the size will be very small. And then for the filtering for the output or input voltage source or output voltage source will be more larger size. So we can decide that, and then we can decide that for the polarized, we can use a little bit larger. So in here we can choose, we need to find capacitor, THT. So THT is through hole, so it will have some like that we can solder. So there is two. And then for the SMD is called, so it's mean that surface mount device. So it will be put on the surface. It will be not have a leg that can be soldered through the hole of the PCB. So right now we will use, for all component we will use THT type. And then so we need to choose C1, and then you can choose many things, but maybe this enough. So TST CP radial 8 millimeter with 3.8 millimeter. We can double click, and then for the another polarized, same. So double click, and then for the C2 we will use ceramic. So we can scroll down this type, and then it should be 5. Yeah, I think 5. So this, so the width between each leg should be 5 millimeter. And for the C4, same. Yeah, you can use which one is as long as 5. Okay, we need a more larger width for the leg. We can use this one, 5, same. Yeah. And then for the diode, because the diode type that we will use is what is called TST type, so it will be used TO220 type. TO220 type. So we will use this one. Double click for the diode, and then for the pin for the MOSFET, we will use pin header. So in here there is size, but majority that you will use is 2.54 millimeter, the width between pin. So we can use 1 times 1. We can use the vertical one like this. So you can see in here vertical, and same for the 1/3. You can see 1/3 vertical like this. And then the input for the input, then the output source, we will use a banana jack. So click connector, and then banana jack 2 pin, double click. And then for the inductor, because sometimes the inductor will be the winding of the inductor, sometimes it will be have a large diameter for the wire, so we can use another banana jack 2 pin for the inductor. And then for the resistor, we can scroll down to resistor. Scroll down. Where is resistor? Yeah, resistor THT. And then we can use I think this one. So 12.7 millimeter. So this is the important one, because it will be the length between 2 pins. This one. Double click. So it will be put for R1, R2, and R3. And then for the potentiometer, we need to go to forget for the maybe on the no, there is potentiometer TST. See, let me make that smaller so I can see. Yeah, so for the potentiometer, potentiometer TST, and you can scroll down to Burns. I don't know how to pronounce, and then use this one, and then double click 3296 W. So click this first, and then click this. Ta-da, ta-da, and then so check in, yeah. And then the last thing is for the TL494. It will be used what is called DIP, DIP sockets. So we can use 16, DIP 16. So this is the DIP 16, but I will use the long pads, so it will be more easier to solder, like this. Double click. Okay, right now you can see all of them already assigned some footprint, so we can just apply save schematic and continue, and then press OK. So we will going back to our schematic, and then after this sorry. Okay, so we back to our presentation. So the step 3 we already done, already finished it, build schematic, and then the next step is, oh, I forgot to this. Yeah, we already do this too, already finished that, and then we need to build the PCB design. So how to build it? We back to our program. So in the schematic in here, there is button in here to open the PCB in board editor. So you can click this, and you will be greeted by this page. And then you need to click this, update PCB with change made to schematic. So it will be following the schematic update. So, and then update the PCB and close, and suddenly you will have some components. So just put it anywhere first, and then you can follow me the design, because I will make this short. Usually I will put the input will be on the left, and then the output will be on the right, and then the MOSFET will be on the middle, and something. So you can follow me like this, or you can follow the design on the slide. So you just put and drag, and then same, you can rotate by press R and on the keyboard. So you can follow me. And then this is for the source, I think. No, 24 volt. So this is for the output. Oh, okay. So this should be for the inductor. So this should be for the output. Input like this, and this is for the input. So we put it, put it like this. You don't need to worry if you use some a large space. It's okay, because this is your first time maybe by building the PCB, so you don't need to worry about that. You don't need to be the design to be pretty or clean. It's okay. I think I made some mistake in here on the schematic, so we need to go back to the schematic, open schematic in schematic editor like this. Yeah, I made some mistake in here. You can see this should be not like this. This should be connected to here. I'm sorry, everyone. So it should be like this, and then you can save again, save changes, and then go back to the PCB editor, and then update again. Update PCB. Tada! Yeah, it should be like this. And then you can follow again. So the placement of the component, actually it will be it depends on your strategy, because our equipment in the lab can only print it can print two side PCB, double side, but right now we will use just single side PCB. So I need to make the design to be jumperless, so I will be not using any jumper. So you can follow my design or on the presentation slide. So you can put like this, and then maybe we need to find the, not this one, we need to find the resistor for the MOSFET. Usually I will put like this. Then we need to warp in, maybe like this. Yeah, and then another pin. Where? Here. Maybe like this. No, it's better to be like this. And then the capacitor for this is for the input. You can just place in here. It's okay. Well, even it has a red mark, you can just put like that. It's okay. And then this, we can place it in here. And this one should be, you can see that when you drag, there is a line between its component. It will be show you the which connection that connected to each other. So you can place it in the more better way. So I think I will rotate this like this, and then put this one on the, so put this one in the ref, so this should be here. Okay, so maybe I will put this. So if it's crossing, you can just rotate, so it will be like this, so it will be not crossing each other. So you can put maybe in here for this one. So I made this to show you how to make the PCB in general. After you learning more and more, you can make it more prettier and then more smaller. So in the end, when you to be a PCB designer, you can have a good skill, because in industries, size is will be size, and the number of component will be decide how much prices that they can sell and then take a profit. So more cheaper will be more better. So that's why you need to design as small as you can. So this is for the C2. We can put maybe in here. It's okay. And then this C for the control. You put like this. Okay, so after everything is put in some places, we can start to put some connection between each component, but we need to make some adjustment how wide the connection. So we can click here and then edit predefined size for the, so in here for the track width, we can click here to add. Usually if you print the PCB on the PCB manufacturer, you can have their minimum track width. Usually is very small, but in this case, because we will print it on our lab, usually I just use 1 millimeter, 0.7 or 1 millimeter for the control side, control section, and then for the high current connection, maybe 2.5, and then we can make some modification later. But first we do this to make more easier. So first, always connect your control side first. For me, no, always connect your main circuit, the high current. So you can use 2.5, and then this crude tracks, click here, and then you can just drag. Oh, and then I forgot to tell you that in this you can choose which side that you will put some tracks, because we will use single side, so we will use only the back side of the copper. So B is for back, F is for front side, back side. So CU is the copper, back copper layer. So click here like this, just click, and we can put maybe like this. This depends on your, we can make more prettier by put something like that, and then we like this. It's okay, don't worry. And then for the 5-volt side, we can put like this, and then yeah, do that. And then this side. So always connect the positive side first. You can connect the ground on the last step. And then for your control, use the 1 millimeter. like this. Okay, so we can rotate this. Now we can connect that thing last. We can choose the other one. So for this one, maybe I will connect it like this. Oh no, sorry, we can undo. We have some way in the middle of the capacitor. Yeah, like this. Tada! And the other things we can connect it. Maybe, yeah, you can connect the ground. It's okay for the control side. And then this one should be connected to here. Then the PWM connect to here. Then this one here, this one here for 24 volt, like that. Then we need to drag. You can connect to there. So you can change, even you already put the tracks, you can just drag and then like this. Yeah, we need to connect this to here. We can make some adjustment. If is it close, we can just click it and drag away. Yeah. So we can put maybe like this. And then the ground for the control, and then this thing source. So is okay. So I forget for the diode to the inductor, like that. Okay, so there is another one that I need to connect it, but I forget. I can do like this. Okay, I think we finished about the control side. So we still have that ground that not connected for the main connection. You can do this thing. First, you draw some rectangle on the circuit, so you can just drag like this, because it's square rectangle. So when we made it, the ratio will be equal. But after you make the rectangle, you can change the size to be close, to be like this. And then right click on the line, and then go to create from selection, and then go to create zone from selection. You will have these pages, and then go to and click ground, And then for the shape, electrical properties, and then specification, you can follow me. Type it like this, and then for the pad connection, choose solid, and then click OK. And then the line will be changed like this, and you click right again on the line, and then go to zones and fill all zones, and let's see what happens. Ta-da! It will connect it directly automatically between ground by full copper, so it will be not wasting any copper. Usually the designer will use approach like this. We call it ground plane like airplane. So this ground will minimize some EMI. Usually it will be on different side to reduce the EMI. So I need to tell you that because this is buck converter, so the current on the input will be more lower than the output. So the output will be more higher current and then lower voltage. So we need to have a bigger wire for this. We can use the same approach for the ground, what we used for the ground before, but right now we will use for the 5V. So you can just draw some rectangle like this, and then you adjust the size to be like this, up to the half of the size of capacitor, and then click right on the line, and then go to create from selection, create zone from selection. So in here we will choose plus 5V. So the pad connection will be same, solid, and then OK. So we have the same line. We can click the line and then right click, and then zone, fill all zone like before. And then I forgot to tell you, if you make the ground zone first before the 5V, both of them will be not, the 5V zone will be not working. So you need to adjust the priority. So there is priority level. Let me try. Yeah. So the higher the level, I'm sorry. So the higher level of the higher level of priority will be, the higher priority. So we need to separate the zone priority level. If the zone between zone is on the same area, like in this example, the 5V will be inside on the ground area. So we need to make some adjustment. So the 5V will be separate from the ground. It will be not connected. So after this, we can save. So this is the finished part of the PCB design. After this, in this software, you can see the 3D design of what you make by press this show 3D viewer window. Tada! You can see general view of your PCB design. You can rotate, and then like this. Yeah, that's all. So I hope that you can make your PCB by following my video, and then you can practice, and then you can make another stuff. I hope that you can send to me the what you make, the schematic, and then the design, the finished project file. You can send to me and I can see it. And if every group can make it, on the next Friday we can make what you already, we can print the PCB from your design that you already made. Okay, so that's all from me. Thank you.